Today we will present the Twin Boomer, Pennsylvania State University's entrant for the Design Build Fly competition in 2021.
Here you can see the dimensions for our proposed final aircraft design. We have displayed the wing area, wingspan, wing chord, and aircraft length and height. Here you can see a 3 view of our airplane. You can note here that the aircraft has a tail dragger with a twin propeller and twin boom configuration. The team also chose to use a high wing and high horizontal tail to reduce the chances of the sensor impacting the empennage upon deployment and retraction. Here you can see our aircraft mission parameters. You can see the weight for missions 1, 2, and 3. It should be noted here that the weight for mission 3 assumes that the sensor is deployed outside of the airplane, so this value does not include the weight of the sensor. And you can also see the static margins for missions 1, 2, and 3. And again, for mission 3, this assumes that the sensor is deployed from the aircraft, but it was also assumed that the static margin would not shift upon deployment since the sensor and the tow cable were both mounted at the CG of the aircraft.
For this aircraft, the team chose two 5-cell, 4,500 milliamp hour LiPo batteries. Each of these batteries also had a high discharge rate. For the motors, we chose two Scorpion 700 kV. For the propellers, we chose 11x7 composite props. And lastly, for the speed controller, each of the motors and battery systems both had 60 amp ESCs. To control the aircraft and all the extra features, we chose a Spectrum 8-channel receiver. And in conjunction with that, we used a DX9 transmitter, which allowed us to program the aircraft to the specifications that we needed. We used a continuously rotating servo to actuate the reel on the inside of the aircraft, and we used Hobby King navigation lights, which were programmable to be used in the correct way on the sensor.
So for the trade studies in the preliminary design process, instead of performing single or multi-variable, 2 or 3 variable trade studies, we performed a 8-variable large-scale design optimization, which follows the architecture shown on the left. And the parameters, wing area aspect ratio, tail arm, tail aspect ratio, sensor mass, sensor length, sensor width, and boom spacing are shown on the right as the final parameters that were used on the airplane. So here is the predicted performance for the aircraft for each mission, including mission velocities and mission scores. As you can see, our airplane leaned heavily into the mission 3 score, as this was found to maximize the total score.
The location that the team chose for their flight test was Midstate Regional Airport. The weather conditions on the day of the flight were 15 knots, gusting to 20 knots from the northwest. This was also at a temperature of 40 degrees Fahrenheit. Seen in this slide is our ground inspection of the aircraft. What you see here is the front view of the aircraft, and in the following slides, you will see the top and side view, which are also in accordance with the 3 view provided at the beginning of the slideshow. Here's a top view of the aircraft, and lastly, a side view of the aircraft.
So from here on, we have our flight demonstrations, including ground inspection. Note the LEDs visibly blinking on the sensor. Note that this oscillation was intentionally actuated by the pilot in order to better release the sensor. Lastly, we have an aerobatic segment for your viewing pleasure.